Hello everyone, and once again welcome to one of my other presentations after a very long time. I haven't been able to post any presentations due to being very busy, but nonetheless I thought that this would be an important time to share with you some of the very important ins and outs of what we call weather. There are many presentations on the YouTube on weather, many nice videos, nice articles as well. The aim of this presentation is not to teach you how weather is formed, like how cumulonimbus clouds are formed or clouds in general are formed and rain and the like. It's just how we appreciate weather when we are flying into it, especially some of us who are turboprop pilots, and we normally encounter weather quite often at our levels, and it's very important to appreciate what weather can do and how we avoid it. The main thing is about avoidance. So without further ado, let's jump into this topic, and I'll just show you one or two things that I've come across and teach you a few little things about measuring the heights of the clouds that we want to avoid. For instance, especially the thunderstorm cells, they call them. And then let's see what more we can understand from this, and I hope that you'll enjoy the presentations. So let's first of all talk of the weather radar antenna on the Dash 8 Q400 aircraft, which I operate, and I am a captain of in my company. So the weather radar antenna is located in the nose of the aircraft. As we all know, those of us who are pilots, we know that in the nose of the aircraft we have the weather radar antenna, and each antenna has got its own specific dimension, and also from the dimension a radar beam width is determined. It will be important and interesting for you to further read on what the beam width is, but of course I'll present to you a diagram and how we use the weather radar antenna to avoid, not to penetrate or find means and ways to penetrate weather, but to avoid weather, to avoid buildups for purposes of obviously safety. So the dimensions of the Q400-8 Q400 aircraft weather radar antenna is a 12 inches, and 12 inch corresponds to a beam width of 8 degrees. For your note, every dimension has got its own individual beam width, and which can also be found on a search. Certain dimensions have got their own beam width. So we use a 12-inch antenna with a beam width of 8 degrees, and about the beam width I'll tell you exactly what it is as we progress through the presentation. So the main thing when we are flying into treacherous weather and sometimes very unfavorable, we need to be making decisions. As pilots, we are trained to make decisions, and decisions come with experience. The more you fly, the more you operate apparently anything, your decision making skills improve. When you confront certain situations and scenarios, you have to be able to decide, and your decisions are based purely on safety. You have to make decisions by taking safety into account. Safety of the equipment, safety of you as a pilot, and safety of obviously your passengers. There is no shortcuts, and there is no time to impress anyone that I can fly through a thunderstorm cell and come out of the other side, because you may not be able to. So safety is of prime importance, and it's a very important phenomenon in as far as everything is concerned, but as far as aviation and flying is concerned, safety is of paramount importance. And when you take decisions, you don't just take decisions on your own. These days, for the past couple of years, decades rather maybe, crew resource management has been introduced and has been very well used by flight deck crew, which also incorporate ground personnel, cabin crew, and the like, operations department, and so on and so forth. So it is not a one-man decision, it is a collective decision that you take. So in the flight deck, you're flying with your colleague, and you have to engage the colleague into your decisions on how you're going to avoid a certain situations which poses a threat to your flight. So once you come to a common decision, you execute the decision, and then you analyze it whether it's working out or not. You never ever take decisions on your own unless you are flying sometimes with an inexperienced person who is just coming in, and obviously you as a captain or maybe a first officer who is way more experienced than a captain need to take a sound decision in order to avoid a certain scenario, situation rather, which can lead you into an unsafe environment. But nonetheless, crew resource management, CRM, is a very, very important method and a very, very important tool for you to avoid bad weather, and also taking it further down to avoid any mishaps that can occur. And it's not only limited to weather, but it's limited right across the board as far as aviation is concerned. So when we talk of decisions, what are those decisions that we want to talk about? I will post a few decisions that we can take or we would take, but these are not limited to anything. There are way more than these that others came across as well, and it will be interesting to know which ones which are not here you guys must have faced and decided accordingly. So I'll just briefly talk about a couple of decisions that I have had to take during weather conditions which aren't favorable to flying. The first one is cancelling a flight. Fortunately, up to now, I have not cancelled the flight because the departure weather for now has always been favorable for me, although it was a bit on the edge, but there was a way to come out of it, keeping safety into consideration. So you can cancel a flight. I mean, there's no harm in that. If the airport of departure is surrounded by severe weather, wind shear, you name it, there's all sorts of havoc going on the airport because of the weather. A thunderstorm is exactly on the airport, or there are certain thunderstorms which are moving one after the other over the airport, and there is no way you can come out of this, then you have to cancel the flight. That is the ultimate decision, and it's better to cancel than to take off and end up in a situation that you never want to be and never come back on the ground. So if you have to cancel a flight, you have to do so. However, this decision has to be taken very carefully, taking all measures into account. Of course, certain things like relocating the passengers and the like is a company problem. It's not your problem as a pilot, as much as you want to keep the company moving, but safety is of prime importance. Okay, it's better to cancel a flight and do it another day instead of doing the flight on a day when you think maybe you could, when you couldn't, and end up in headlines. You don't want to do that. Okay, so canceling a flight can be one decision. Another decision is a very common one. You can wait until the weather passes. So if you're on the ground, you will say, okay, I'll not start my engines. I'll see first of all how the system of the thunderstorm is moving. Once it is over, it's gone at a good distance, I may have some clear spots for my departure ahead of me. If you're coming in for a landing, you can hold. You can definitely hold over a particular point. If you see your weather radar screen doesn't look that great, it's got a lot of paintings on it, you know that okay, there is maybe a weather overhead the field, and in consultation with the air traffic controllers of that particular airfield, you can decide that okay, I'm going to hold for maybe 30 minutes depending on how much fuel I have. Obviously that's the main thing, is fuel in these situations. I can hold over a particular fix, give it some time, let's see how the system is moving, and once things look a bit better from ground perspective, from your perspective, you may attempt an approach and see how it goes. If you feel that no, it's not something worth it, you keep holding a bit more, but eventually a heavy thunderstorm over an airfield wouldn't take more than 45 minutes to go, unless it's something of a different sort. Nonetheless, delay is a very good decision as well. If you have delayed enough and you think, okay, I'm not going to be able to make this, then you divert. You can obviously program your aircraft and say, this is not going to work out for us, let's go to another airfield, wait and see how the situation comes up on our original destination, and we come back again. So it's another very important decision to make, is to divert. Another scenario you may get is that, for example, if you are descending into an airfield in the terminal area, you may want to use headings, LNAV heading select, or rather, which is a descent, is the most commonly used function of the Q400, because you don't lose your VNAV profile. You can even use vertical speed to stop your descent. Maybe you just want to go over a bit of a cloud, and then you want to continue descending after you pass the cloud. It's all to do with judgment, so you are able to even adjust your descent profile. So these things come, the more you fly, the more you meet the situations, and the more you are comfortable with using the flight guidance control panel modes, the FGCP modes they call them, to fly safely. Another decision you can make is, do you have to change the runway? Maybe you should. Maybe you want to depart from a runway ahead of which there is a build-up. Okay, so you might say, okay, if I take off from here, I may end up straight into that build-up. So why don't I use maybe the opposite runway? All right, let's say you come taking off from runway, let's say 14, okay, and the opposite is 32, and your routing after departure from 14 is a right-hand turn. But if you see ahead of your runway, right ahead in front of you, you see a weather build-up. But if you see the opposite runway, let's say runway 32, which is reciprocal of 14, that side is a bit more clearer. So why not take that runway and change your routing to pick up your departure course when you're airborne? Pretty much simple. You can definitely even do that. Of course, it all depends on the winds, but if the winds are favorable, if the runway is long enough, all right, you can also use your supplements to take off into certain tailwind conditions for the Q400, that is. I'm pretty sure other aircraft also accommodate certain tailwind takeoffs, keeping safety into account. So runway change is a very important one. Okay, so you must always consider changing the runway if you have to. Request headings. If you have to request headings from radar, you can do so. Altering the routing. So let's say, for example, from your present position you are going to A, then to B. But if you're going to go to A, waypoint A, there is weather there. But if you direct to point B, you can circumnavigate the weather. You can use your FMS to do that, as long as you request the control authority of that area that I cannot make it to A, I can only go to B. It's also a very good decision, okay, because you'll keep yourself away from the weather. So all these are FMS manipulated, or you can even use FGCP to manipulate your routing. All right, changing approach on a runway, the same as what we just talked about a departure. You're coming in on a particular runway. On that side of the runway, approach sector side, you have a lot of weather. But if you see the opposite runway, the weather is not that bad. So you can always request for landing on the reciprocal runway. Okay, again, wind dependent and the like. So these are some of the decisions, and the main one is that if you are already into your final approach and you're going down and you see that, okay, now things are becoming a bit funny, there's a bit of winds picking up and the like, and you know that your approach will become unstabilized, then you'll execute a go-round. And a go-round is the best decision a pilot can ever make. It is not subject to any penalty. You go round when you think I'll not be able to make it. So the whole point here is to understand that you don't force yourself into a corner. If you cannot make it, you'd rather be safe. You are not there to prove that you are brave by fighting nature. You cannot do that. So just remember that these are some of the points that I've come across. I may have missed quite a few, and I'd really appreciate if a couple more were posted. So just to share as aviators, so we can know who has experienced what in their flying. Okay, this is the important part. Whenever you take decisions, safety comes first. You don't prioritize your bosses, you don't prioritize anything, you prioritize yourself and your safety, because by doing that you are going to keep your company in a safe manner. Okay, so very important is safety comes first. So please remember, this should be printed in your heads and hearts. Safety comes first. Okay, so now what we can talk about is certain things that people tend to do to force themselves into corners, and you have to always say no to things like time pressure. If you are delayed, for example, it's not your problem. You might have been delayed due to circumstances which are beyond your control. You do not need to meet time pressures. Okay, there has been an incident in Zambia. You might have even actually come across it on YouTube, where a Q400 was flown into severe weather, ripped apart just because of time pressure. You might see this clip on YouTube. It's under the name of ProFlight, and if you search for this, you will actually see how it has been explained. So time pressure is a very, very dangerous thing to abide to. As much as we want to keep time, yes, as much as we want to keep our schedules, yes, but when it comes to weather, you've got to be relaxed. You've got to first of all consider safety. So another one is a phenomenon called get there it is. Get there it is a phenomenon which in simple terms means that you want to get to a point no matter what. Okay, so you want to cut corners, you want to go through a thunderstorm, you want to fly upside down, I don't know what. Okay, but you want to get there just to meet your schedules. This is a very, very dangerous phenomenon and a very, very dangerous habit that as pilots we can actually do. You don't need to do this. Okay, when conditions are unfavorable and you know safety is under question, you do not attempt to proceed with a flight when you know that things don't look good. Safety, safety, safety. So avoid this phenomenon of get there it is. Give yourself time to assess, analyze, discuss with your fellow team, and then you come with a common conclusion. Okay, there is no harm in doing that. It's better to be safe. When weather strikes, it strikes very badly. Weather has no mercy. Weather will be there in front of you. You have to avoid it. Weather won't avoid you. You have to avoid the weather always. Okay, and the other one is a very important one called complacency. People who have flown for many years, okay, they think, no, we can do this, it's fine. There is no such things. Okay, you don't push yourself into a corner and say, okay, I'll take this much fuel, when you know you could take more fuel, and then you end up in a minimum fuel situation, and you run out of fuel, worst case scenario, and things go wrong. So complacency is a very, very bad attitude when it comes to flying. You must always be safe. Don't think, no, I'm okay, I'm a Marco person, I'm a daredevil. You are not there to prove such certain features. Okay, you are there to be safe for the purpose of the equipment you're operating, for the purpose of the company you're flying for, and for the purpose of your passengers. It's very, very important that you keep safety first. All right. In the forthcoming slides now, we're going to just discuss briefly about the weather radar and the images. This table here, which you'll get it from the AOM of the Q400, will just tell you how to interpret the paintings on the weather radar. So this is one of the weather scenarios I actually met when I was coming into a particular airport. This is real. This is a real-time image, and you can see from the way it was horrible. Like everything was present in this weather phenomenon. There were heavy thunderstorm cells everywhere, and we had to navigate. We circumnavigated it definitely, but this was the very, very severest weather near the airfield that we were coming into. Okay, so I've taken this picture just to show you what the table means. So for example, the green part shows you that the rainfall, by the way, the weather radar reflects moisture. It reflects off rain. It does not reflect off just simple clouds or the way there is no moisture. It reflects off heavy rain, which is reflectable. If that's it has got good reflectivity, rather, that would be the better English to say, and then paint the picture. So if the millimeter per hour is 1 to 4, it will be green. That's not too bad. And in green areas, you can definitely fly them. If it's purely green, it's flyable, sort of. There'll be a bit of bumps, but it's flyable. The yellow areas is where the millimeter per hour, meaning the rate of rainfall, is a bit more higher, 4 to 12. So here you do feel a bit of choppiness when you enter these ones, and you don't want to actually enter yellow regions. I'm not saying that you can't fly through them. Yes, you can, but I don't think it's worth it if you can avoid. And obviously red is very heavy. It could be a lot of turbulence, a lot of heavy rain in there, maybe with hail. So you don't want to actually even go into red. Red is just a no-go. And magenta is basically turbulence. That's where you really don't want to go. That's actually in the core of the system of thunderstorms, okay, where there is a high speed, extremely high speed, 6,000 foot per minute to 4,000 foot per minute updrafts and downdrafts when you read about them. And those are like machines, like hacksaws or saws, if you want to call it. And if you enter that region, I don't think it's very nice at all. You don't want to go there. It's just a no-go area, okay? A bit on the reddish area, sometimes when you're coming into land and you have a complete red image in front of you, but you can still see the runway ahead of you. As long as there is no active thunderstorm above you, leading to what you call microburst phenomena, which you don't want to go into, it's just a pure rain cloud, like a flat rain cloud, which is giving off a lot of rain, is going to paint red. This can be flyable because you have the runway in sight, number one. Number two, on top of you, you've verified that we don't have any active thunderstorm which is going to lead to a microburst. So this is perfectly okay to fly. I've gone through some of these and it was very okay, but you still have to assess. You don't just go straight in and say I'm going to make it through. Best ways to avoid, if you can avoid. That's the main thing. Okay, now these are some pictures that I came across when I was flying, and you can actually see how it was. The first image here is basically lined up on the runway center line, and the routing was, if you can see the cursor, go to the beacon and then turn right. All the weather was towards the, I can say, southeastern side of the airfield, looking at the compass rose directions. Okay, it was all this way, and we were planning to go right to our destination. So this was completely okay to depart because the weather was quite far off our course. The second image was in the cruise, and you can actually see the weather system right in front on our path. We had to avoid this one, and there were a couple of cells. We could see them from the window and we could marry them to the images, and we wouldn't want to go that far at all. The third image here is when we are coming in to an airfield, all right, and the weather was all around, as you can see, completely trying to block us. So at a tilt of 1.5, I'm going to be explaining to you about these angles in a moment on how I understand them after studying the tilt and how to use a weather radar. I'll make it more simple, and I'm pretty sure it's the way it works, but you can read most of the articles on this and others on other platforms. You can see the weather here at 1.5 degrees was looking like this, and then what you should understand is that there is something called pattern changes. So when you are flying towards weather systems like thunderstorm cells and clouds and all that, what you see from far out isn't what it is when you approach closer. Believe you me, I've appreciated that. From far out, a thunderstorm may look like one bulk, one mass of thunderstorm, but as you're coming closer, you might now try to divide and see, okay, it's made up of a couple other cells. So the pattern changes are very important to appreciate. Every time the pattern will be changing, the closer you get. So it's very important don't to just rely on one pattern, and that's the reason why we use the tilt function of the weather radar, and I'll explain to that in brief as we progress through the presentation. Now this third image here was then made into this one here, the first one on this slide, when the weather radar tilt was 2 degrees up. Okay, so now you can see that in the previous one there was a lot of cluster here, but now with 2 degrees up, at least because we are descending, we could isolate some of these buildups and we could appreciate them even seeing outside how they look like. And it was completely okay to circumnavigate these ones and come in for the landing. It was quite a lot of weather in this airfield when we came in that day, I still remember. And this one here was another very bad one, where the landing runway was not where we are going now, it was the other one, but decisions made it possible that we couldn't never go to the right hand side of this image, as you can see, because there was complete weather here. It's very obvious we don't want to fly into all this, so we decided to change the runway and come and land on this side, although we faced quite a bit of difficulty here, but it was a bit better than coming in on the opposite runway, which was originally assigned. We had to request to use a different runway, and the wind wasn't that bad as well. So that's what we call decisions and the like. Now, very important tool that we have on the aircraft, and of course in certain airports you have also radar, which also can see weather around the terminal area, is the weather radar. So the weather radar, I'm not going to go into complete details of the weather radar of the Q400, it's not this part of this presentation, but how I and how my colleagues and how we in a company could use. And remember that this is just our own way of using, and everybody has got their own way of using weather radar. As long as it shows you what the reality is outside, you're completely safe. But you can read more about the weather radar on the AOM, and then there is a tilt function and determining top of cloud height, which I want to go into. This is a very important one, especially for us turboprop pilots. It's very important, even for jet pilots. Of course, when they come into lower levels where the turboprops fly, they will need to use certain techniques like these. And these are some of the functions that you can actually consider in how to use weather radar. Very important is AOM. AOM has the aircraft operating manual, they call it, has got everything about the weather radar of every aircraft. We're going to talk of tilt function in a moment. Before you depart, you can actually even visit satellite images, let's say on significant weather charts. So there are certain presentations that have been given on YouTube on how to interpret satellite images, and PIREPs are pilot reports. They can even tell you how high a particular cloud is on the approach sector of a particular runway and the like. So all these are helpful tools that you ought to use in order to make decisions. It's very important. And yes, significant weather charts are also a very important tool to before you fly, you have to actually investigate how the weather looks like along your route. We're not going to talk of all these, the first one, the third, fourth and fifth one. These are just for you to research. I am basically going to consider and just tell you how the tilt function of radar can be used, weather radar can be used to determine how high the cloud is in a specific range. So without further ado, let's try and look at that and see how it is. So tilting the weather radar is, as I said, this is not a prescribed method. Different pilots and companies will have their own techniques, but otherwise manuals of all weather radars tell you similar things, and it depends now on you on how to utilize it. Alright, so on departure I normally set my weather radar to 5 degrees to 5.3 degrees, somewhere around there, so actually I can see up, and I'll tell you what these angles mean when we actually want to, when we're in the cruise and want to determine the cloud tops. In this particular presentation, or in this particular explanation rather, 5 degrees simply means you have tilted the dish in the nose of the aircraft by 5 degrees, so you are seeing above you what you expect to see on departure. Okay, so it just tells you how intense whatever it is. During climb, we now start reducing gradually to further on, just before you reach top of descent, top of climb rather, my apologies, top of climb, you can keep it 2.3 thereabouts. So it gives you a better picture what's ahead of you. And during cruise, in weather situations, I normally play around with the weather tilt from 1.3 to around 2 degrees to scan around the region, and I'll explain to you how this works in the cruise. And in descent, we are normally interested in the weather above us mostly, because we are leaving all these thunderstorm cells and or clouds, heavy clouds above us, so we actually just keep it tilted up a bit to 2.3 is very good. I've seen that it works out for me, so I can see what weather awaits for me if there is any weather above me during the descent, approach and landing. So these are some of the values. As I said, these values are not prescribed, they are just depending on the convenience. Okay, and you might have your other methods as well, which will be very useful if you can even comment, so that people can use it to their advantage. Now, the radar beam. Let's study the radar beam. As we have talked of weather radar, the weather radar basically uses microwave technology, most of them, to send out a beam which is in a flashlight type of pattern. Alright, so the beam covers a certain distance, okay, and it reflects off objects in front, objects meaning the clouds and the like, and the moisture, precipitation, and brings it back. Okay, operation and technicalities of the weather radar are not the scope of this presentation, but just how we interpret the weather radar beam. So the beam is a cone-shaped pattern with a center line, the blue line, which is very important in our case here, which we'll be referring to as we go along. So this angle here is called the the beam width. You remember that Dash 8 Q400 I told you a while ago has a 12-inch dimension, and a 12-inch dimension has got an 8-degree beam width. And as I said that the inches and the beam width are inversely related, meaning that if it's a larger dimension, the beam width is smaller, and vice versa. You can read about them, and the larger the dimension, the better the reflectivity characteristics of weather radar. Okay, the smaller the beam width, the more sharp it is. That's a very important point to note. Okay, so now a couple of other angles here. Basically, because the blue line is a halfway point, so sorry about that, I just had to actually, the blue line is a halfway point, so each of these sections here are divided into 4 degrees to make 8 degrees, and we are definitely going to use this half beam width number for our weather radar in order to determine cloud tops. Okay, so how does it work? Here's your aircraft in cruise flight. It should be in cruise flight. It's just an image which I've taken and I've put it there. And here's your center line, the horizontal line from the nose of the aircraft. Okay, the horizon, if you want to put it that way, the artificial horizon. Now, what we've done here, if you can see in this beam, weather beam, the bottom part is not shown because it is actually coincided with the horizontal, the black dotted line, dashed line. Okay, means that we have tilted the weather radar beam by 4 degrees. If you remember, each of these angles here is 4 degrees. So now we have actually tilted this by 4 degrees. The tilt is measured from the center of the beam to the horizontal. Okay, that's very important because we're going to use simple trigonometry, high school trigonometry, to explain how it all works. So this is our 4 degrees tilt. Okay, and when we continue with the weather radar explanation, we definitely jump into something called the 1 in 60 rule. I'm not going to go too detailed into this one. It's a very simple rule. You can actually read about it on the web, or if you have your manuals, you can even read about it on your manuals. So what does a 1 in 60 rule say? If you have a right angle triangle, you are here at the corner where my cursor is. It says that if you are 60 nautical miles away from a particular point, let's say a VOR or any particular point, and you are 1 degree off course, so you were here, then you ended up there, traveling 60 nautical miles. The 1 in 60 rule says you are 1 nautical mile off track. This is an obvious rule which we all learn at flight school. Okay, I want you to revisit it if you didn't know what I'm talking about here. And then 1 nautical mile as a conversion is equal to 6,080 feet. Call it 6,000 feet. As pilots, we like approximating. I'll make an emphasis in a moment. Now, looking at this, what I did, I made a table. I went to Excel and I tried to investigate a couple of tilt angles, okay, and at certain ranges, how they would give us how far above us the clouds are. That's the main point here. So here we're not looking laterally, we are looking at vertically. Remember, it's a vertical situation, not a lateral situation. So the top row is certain tilts. 4 degrees was just basically the one where we keep it flat, and then we increased all the way. Now when I reached 5 degrees and beyond, I was seeing a pattern here which I'd like you to appreciate. Very important. If you look at this 5 degrees here, the 5 degree tilt which is displayed on your ND, or your MFD rather, is actually a 1 degree off track. Okay, because you remember in the previous scenario, if I can just take you to the previous slide, yeah, means I have to do all this. Your tilt is meant to be 5 degrees. So if you go up 5 degrees, you've got to subtract this 4 degrees from the 5 to make it 1 degree. Okay, this is 4 degrees here, but if I continue raising the whole beam, which you'll see in the subsequent presentation, you'll come to know that 1 degree corresponds to 5 degree tilt. You are subtracting the amount you have tilted by, and you are subtracting that amount from it. You are subtracting the half of the beam width, which is 4. Okay, I'll show you in a picture in a moment. If you look at the green column here, at 10 nautical miles, 1 degree is almost 1,000 feet. 20 nautical miles is 2,000 feet. 40 nautical miles is almost 4,000 feet. 60 nautical miles is 6,000, and so on and so forth. You can clearly see that if you can add 2 zeros to each of these ranges in nautical miles, that will convert into how many feet above you the clouds are. Okay, that's very important. This is just a very important approximation on determining cloud tops. So now let's say you now tilted 6 degrees up. 6 degrees will mean how many degrees off track? Exactly 2 degrees. So for 2 degrees, now you can see, you'll times this whole thing approximately by 2. This will become 2,000, 4,000, 8,000, 12,000, 16,000, and around 25,000, 24,000. Can you see what's happening? If you go up by 7 degrees, so when you turn the knob to 7 degrees, how many miles, of course, how many degrees are you tilting above the cloud top? It will be 3 degrees, because 7 minus 4 is 3. So you'll times all these numbers approximately by 3, and you'll be getting approximate numbers here. Okay, so these clearly show the 1 in 60 rule application. I'm more mathematical because I'm a mathematics teacher by profession as well. So I don't just like reading something without getting the mathematics of it. So it's very important. Now we don't use these numbers in this way. These are very exact numbers created on the Microsoft Excel spreadsheet. But we as pilots, we don't have time to use complicated numbers. So what we normally do, we always approximate. Okay, so at 10 nautical miles, a 1 degree tilt will be 1,000. Okay, at 20 nautical miles, a 1 degree tilt will be 2,000. At 40 nautical miles, a 1 degree tilt will be 4,000. Similarly, at 10 nautical miles, a 6 degree will be 2,000, because 6 degrees is 6 minus 4 is 2 degrees off. So, and so on and so forth. At 7 degrees, is 7 minus 4 is 3, it will be around 3,000. I hope this is making sense. If it isn't, in the comment section you can comment and I'll come back to you if you want more explanations. But there are many such explanations given by other presenters on the same issue, which also may be helpful. But this is how the 1 in 60 rule is applied. Okay, moving on. Now we can see this scenario better. Here's our aircraft in cruise. Now in front of the aircraft we see a thunderstorm cell. Now we want to know how high it is above our level. So if I bring in the diagrams, here is my tilt now. You can see the bottom. The main component of the weather radar beam is the bottom line, the bottom beam. Okay, there are two beams here, okay, which form into the cone at the end, the top beam and the bottom beam. So once the bottom beam has been raised such that the pattern on the weather radar display disappears, that's how high your cloud top is. Now let's see how it works. So this is basically your tilt angle, all right? But remember, don't forget this half, because we're going to be using this right angle triangle here. If I can do it this way, let me just put all these values in, then you'll be able to appreciate. So our right angle triangle is basically, if I can present this, it will be very important. This is our right angle triangle. Can you see that? Okay, so it's all from here, from the nose of the aircraft, bottom beam, top of the cloud, and then that's your right angle triangle. So you are mostly interested in the angle that is below the bottom beam. Okay, so how do you work that out? It's very simple. You know that this angle here is 4 degrees. You have tilted this all the way up, let's say 5 degrees if you want, or 6 or 7, and the cloud disappears at one of those values. So you'll have to remove 4 from that angle to get this angle here, which is the tilt angle minus 4. I hope that makes sense. Okay, so once you have done that, you will be able to understand what's happening. Okay, now what we come here with is that these are the 4 degrees I'm talking about. Now we are at flight level 250, for example. Okay, that's flight level 250, 25,000 feet. How high is the top of the cloud? So let's work it out. Let's see if we can work it out. So let's say, for argument's sake, our range is 80 miles. So this whole distance was 80 miles. 80 miles we saw a painting on our radar ND image, and we tried tilting it all the way to 5 degrees. So when we reach 5 degrees, this whole thing here is 5 degrees. Okay, we raised the beam, the whole cone-shaped beam, as you can see, has been raised by 5 degrees. All right, now 5 degrees tilt is actually 1 degree off course. Okay, so it's 1 degree below the bottom of the bottom beam, all right, with respect to the horizontal, the dotted line. So that's what I've said there. And now 1 degree off is around how much? At 80 nautical miles will be 8,000. If you revisit your table, okay, it's around 8,000 feet above the aircraft. Okay, so it's very important that you understand these analogies. You remember at 1 degree at 40 nautical miles was how much? 4,000 feet. So 1 degree at 80 nautical miles will be times 2 is 8,000 feet. Approximations. So above the aircraft's altitude, this cloud is 8,000 feet above. So how high is it in total? You add 25,000 plus 8,000. So this cloud is actually 33,000 feet. The top of the cloud is 33,000 feet. It is clearly in your path. You do not want to go that far. That is how we actually use the tilt function. But more of it you can actually get the more you read and the more you research on other platforms. This is basically my understanding and explanation on how the weather radar tilt can be used to determine the top of the cloud. Okay, how high the top is in relation to your level. So you can decide, am I going to clear it or am I not going to clear it? Okay, so very important when it comes to weather is avoidance. You are not there, again as I say, to squeeze yourself in a corner thinking it's okay, I will go through here, I'll go through there. You may not. It's better to avoid. And what do they say? Thunderstorms must be avoided by 20 nautical miles laterally or more, and if you can avoid them from the top, which is unlikely most of the time, 5,000 feet vertically. This can be done by jets, but some of us who fly turboprops, we are limited to our ceiling. So vertical avoidance is a bit unlikely, but horizontal avoidance is mostly very, very likely. Okay, so very important you understand this point of mine in order to keep safety. All right, and to avoid, you can use heading select. Okay, in the climb I use heading select to avoid, even sometimes in the cruise if I have to, and then I can be using my DTO function and the VTO function to program my lateral and vertical profiles. Okay, LNAV heading select is a very important way to avoid thunderstorms as well, especially maybe in the descent phase most of the time, so you lose your vertical profile. So normally I go LNAV heading select, and then to keep my aircraft anchored to the waypoint I'm going, I will do DTO to the waypoint and immediately go to LNAV heading select again. You see, so in that way I don't disconnect my VNAV profile, which is okay, I can even reprogram it, but I keep doing this to keep myself anchored laterally and vertically. Alright, because you know that the VNAV profile disconnects at around 12.5 nautical miles laterally on the Dash 8 Q400. So LNAV heading select is very important, and also you must know in this aircraft, the Q400, the one I fly, VNAV won't engage unless an LNAV mode is engaged. So LNAV itself, LNAV heading select, LNAV intercept are three of them which need to be there for the VNAV to be there. Alright, so you can even use this using radar vectors as well. The DTO and the VNAV VTO functions are very important to keep you while you are deviating, avoiding the weather in the descent towards your airfield of landing. You can be continuously reprogramming your lateral and vertical profiles. Okay, vertical speed can be used in case you really want to descend quicker through a particular build-up, or maybe reduce rate of descent and reprogram again. So these are all tools for you to avoid weather. The all function can be used. Let's say you are coming into descent, you just want to stop the descent momentarily, then you want to go back down again, you can stop the descent. All right, and you can even modify your FMS route, okay, so that you are within the safe parameters of the airfield and also of your approach. Is very important. Right, so other than that, I want to say that this is the end of the presentation on weather. And once again guys, just remember, weather has no mercy. Okay, and don't be complacent, don't abide and bow down to time pressures. All right, don't bow down and abide to management pressures. Okay, because you're up there, your job is to keep your equipment, your passengers and yourself and your other crew members safe, and avoidance is the best way to do so. I cannot emphasize this phenomenon of avoiding weather as much as you can, using all necessary well-informed decisions taken collectively between you and your fellow crew members. Having said that, till the next time, happy landings, always be safe, and please do make any comments that you feel you should. It will be much appreciated. Thank you very much. Bye bye.